Trig ratios are really useful for making calculations using triangles, and it's amazing really how much you can do with just using similar triangles and trig functions, making calculations that give you really good approximations or fairly good approximations of, for example, the distance from the Earth to the moon and stuff like that. But there's something much deeper and much more useful that these trig ratios can do for us. People realized that you can use these trig ratios to describe and to analyze periodic phenomenon. If you think of electromagnetic radiation, we think of that as moving through space in waves. It's a nice periodic wave. We can define that using trig functions, and once we define that, we can analyze it. We can make predictions with it. We can do a lot of manipulation with it. But it all starts with defining something that can model that wave. So we need a function that gives us a graph of that wave, and trig functions will do that for us. So far, we have trig functions defined for right triangles. So in a right triangle, you've got a 90-degree angle, and then the other two angles add up to 90 degrees. So if you think about the trig functions as like sine of, let's use the variable theta, the Greek letter theta for the variable, sine of theta, cosine theta, tangent theta. That theta could be any angle between 0 and 90 degrees. Can't be more than 90 degrees because we're working with the right triangle. It actually can't be equal to 90 degrees or equal to 0 degrees if we're working with the right triangle. So what we have is some functions whose domain is from 0 to 90 degrees. We want to take those functions and extend them to have an infinite domain. And that's what will allow us to model these periodic phenomena. So let's start with sine. If we take, say, sine of 150 degrees, we don't even have a definition for that yet. So what we're going to do is we're going to look at the angle 150 degrees. So we'll start at the positive x-axis, wrap counterclockwise to 150 degrees, and then we want to be able to say what sine, cosine, tangent, and so forth are for 150 degrees. And the useful way to define this so that we can get the kind of function that we want to model periodic phenomena, what we're going to do is we're going to let sine of 150 degrees be sine of the angle that you get when you take 180 degrees minus 150. So it's the angle between the x-axis and that terminal line that you get from 150. So you wrap around from the positive x-axis to 150, and then if you take the angle that's left between the x-axis and 150, that's the angle that we're going to use. It's called a reference angle. And so sine of 150 degrees will be sine of 30 degrees because 180 minus 150 is 30. Cosine of 150 will be almost equal to cosine of 30 degrees. But since it's on the left side of the y-axis, we'll say that that x value is negative. So cosine of 150 is the negative of cosine of 30. And then tangent is y over x. So the y value is still the same as it was before. The y value is still positive. The x value is negative. So tangent is going to be a positive divided by a negative. So tangent will be negative as well. If we want to do this with other quadrants, we can. So for example, 150 took us to the second quadrant. If we go down to the third quadrant with, let's say, 210 degrees, then our reference angle that we're going to use this time is the angle between still the x-axis, and this time we've gone 210 degrees. That takes us 30 degrees below the x-axis. So the reference angle this time is again 30 degrees. and it's again the angle between the x-axis and the terminal line for the angle. So if we wanted sine of 210, that would be almost equal to sine of 30. The reference angle is 30, but the y values are negative in quadrant 3, so sine of 210 would be minus the sine of 30 degrees. So in quadrant 3, y is negative and x is negative. The radius we will always consider to be positive. So the hypotenuse in these trig functions, or the r, will always be positive. So sine and cosine in quadrant 3 will both be negative, and tangent will be a negative divided by a negative, so that will give us a positive. And then if we bring it into quadrant 4, like let's do 330 degrees. So that takes us almost all the way back to the positive x-axis. It would take us all the way back, except we would have 30 degrees left. So the reference angle for 330 would also be 30, because we're again going to take the angle between the x-axis and the terminal side, the smaller angle, the acute angle. So cosine of 330 will be equal to just cosine of 30. And sine of 330 will be the negative of sine of 30, because the y value in quadrant 4 is negative. And then if we took tangent of 330, since tangent is y over x, and the y value is negative and the x value is positive, that means tangent of 330 will be negative. So tangent of 330 is minus the tangent of 30. So you can do this with any angle from 0 to 360 degrees, and you don't have to stop there. You can keep going on forever. You can wrap around as many times as you want. So like if we wanted to go all the way to 400 degrees, we'd wrap around once to 360, and then we would need to go 40 more degrees. So sine of 400 degrees would just be sine of 40 degrees. If we wanted a negative number for our domain, instead of wrapping clockwise, we would just instead of wrapping counterclockwise, we'd wrap clockwise for negative angles. So for example, if we want sine of negative 90, that would be the same thing as sine of positive 270. And let's say sine of negative 30 would be the same thing as sine of positive 330. Doing this, we can extend the domain of our trig functions out forever to the left on the x-axis and forever to the right. So we get an infinite domain for all of our trig functions this way.